Hi, I'm Sepideh. I'm an ICPC alumni. It's great to be here. I do research on algorithms for large data, and today I'm going to tell you about them, and in particular the notion of composable corsets, which is a technique used for data summarization. Okay, so when we work with large data sets, classical algorithms are often too inefficient, and new models have been developed to capture various aspects of computation over massive data. For example, the input to our algorithm might be so huge that the algorithm can't even read the whole input. And sublinear time algorithms is a model of computation that is designed for this case. So here the algorithm is allowed to make queries to some parts of the input and solve the problem approximately. Okay? And so this is a little bit similar to interactive algorithms that you might have seen. So the algorithm can make queries to parts of the input, and the total number of queries is what we care about. And even if the algorithm can read the whole input, there may not be enough memory to store all the inputs in the main memory. So in the streaming algorithm is a model of computation to capture this aspect. So here we assume that the inputs to our algorithm is stored externally somewhere else, and the algorithm can make one or few sequential passes over the input and needs to solve a problem using sublinear amounts of memory. And so maybe it can only use like square root n memory or even log n memory, but it should still be able to approximate the solution. Okay, and even if the algorithm can read the whole input and store all of it, one machine may not be enough to do, let's say, all the n cubed computation, okay? And so parallel algorithms or distributed algorithms are models of computations that are introduced for this case. So here the data is partitioned over multiple machines, and the machines need to interact with each other to solve the problem over the union of the data held by all machines. And actually this list continues. There are also techniques that are particularly helpful when we work with large data sets. For example, suppose that we have a large data set of number of points in a high dimensional space. Okay, so maybe we have 1 million points, each of them in a 1,000 dimensional space. And so this is a large data set, and you can think about summarizing this data in two ways. So maybe we can try to reduce for each point, maybe we can try to reduce the dimension of the points. That is, we want to approximate every point with a point in a lower dimensional space while preserving the relation between the points approximately. Okay? And it's known that for a set of n points, we can always reduce the dimension down to roughly log n while preserving the distances between the points approximately. Okay, and you can also think about summarizing this data set in another way. So basically, if there are 2 points that are very similar to each other, then maybe we can only keep one of them. There's no need to keep both. Okay, so corsets is basically a notion that is capturing this concept. So corset is a subset of the data. So here, a subset of the points that is a good representative. Okay, a small subset of the data that's a good representative. And there are other techniques, for example, sampling, sketching, and so on. And but today I'm going to focus on the notion of corsets, and in particular the notion of composable corsets. So let me start the main part of the talk by telling you what a corset and a composable corset is. Okay. So a corset is a small subset of the data that's a good representative. Okay, so what does it mean to be a good representative? Basically, if we have a problem that we would like to solve on a data set, then basically if we can solve the problem on this small subset and this gives me a good approximation, then I say that I have a corset. Okay, so mathematically, basically, if suppose we have a function f that we want to optimize on our data set, then if the value of the function f, or the optimal value of the function f over this small subset approximates the value of the function f over this over the original data set by this factor alpha, we say that we have an alpha corset. Right? So to give you an example, suppose we have a set of points and we want to find the 2 farthest points. Okay, and so we know that the 2 farthest points always lie on the convex hull of the set of points, and therefore the points that are on the convex hull form a one corset for the diameter, that is preserving the value of the diameter exactly. Okay, so the problem with the convex hull is that its size is not necessarily small, right? All the points could lie on the convex hull. So we're looking for corsets that are provably small. The size of them are provably small, but at the same time they can provably have an approximate solution. Okay, so corset is, as I said, it's a generic notion, and many variants of corsets exist. And today I'm going to tell you about the notion of composable corsets, which is basically a corset with the composability property, meaning that the union of corsets, the union of multiple corsets, should form a good summary for the union of the original data sets. Okay, so again, let me be more specific. Suppose that we have multiple points as v1, v2 to vm, and we have a function f that we would like to optimize on the union of these data sets. Okay, then we say that subsets u1, u2 to um form composable corsets for these points if we have the following property, that basically if we remove all the points but the ones that are in the corset and take their union, then the value of the function f over this union approximates the value of the function f over the union of the original data sets. And if we have this by, let's say, an approximation factor alpha, we say that we have an alpha corset. Okay, so I'll tell you some examples as we go later in the talk, but for now let me focus on this composability property and tell you why this composability property is important. Okay, so in fact, if we have a composable corset for a task, then this automatically means that we can solve the same task in other massive data models of computation. So let me explain. So first suppose that we are in a distributed setting. So we have multiple machines. Each machine holds part of the data, and we want to solve a problem over the union of all the data held by all machines. Okay, and suppose that we know that the problem that we want to solve has some composable corset. There is an algorithm that can compute a composable corset for it. Okay, then basically each machine can just compute this small summary on its own data and send this summary to a single aggregator. So the aggregator can then compute a solution for the union of these summaries that it has received. Because of the composability property, the solution that is computed at the end is a good approximation for the union of the data held by all machines. And because the corsets have small size, the total communication is low. Okay, so if we know that the problem admits composable corset, then suddenly we can solve it in a distributed setting. So the next application is to streaming setting. Okay, so as I said, in the streaming model, the data is stored somewhere else, and the algorithm can make one or few passes over the data and solve the problem on the fly using limited or sublinear number storage. Okay, so now again, suppose that the problem that we would like to solve admits composable corset. Then basically what we can do is as follows. We can just divide the input or the stream of input into chunks of, say, size square root n. And then the algorithm is making a pass, so it's start receiving the first elements one by one and store them in the main memory, okay, until it receives the first chunk completely. Okay, and then it can just compute a composable corset for the first chunk and then discard the elements in the first chunk and only keep the corset. And then it continues to the second chunk. It stores all the elements in the second chunk in the main memory until it receives all of it, and then it computes a corset for that and discard the elements. And it repeats this process until the end of the algorithm, and it only keeps the corsets. At the end, it just computes the solution over the union of these corsets. Okay, and basically this allows the space usage of the algorithm to go down from n to roughly square root n. And again, because of this composability property, the solution that we computed at the end is a good approximation for the solution over the whole input. Okay, and in fact, this corset has been used in different settings. For example, to improve the runtime, we can just divide the data. We can just run the corset on each part, and then we can basically do a divide and conquer type of algorithms. Okay, so we have shown that basically how we can get such summaries for specific optimization problems. We have also shown that not all problems can admit such efficient summaries. Okay, so for this talk, I'm going to focus on the diversity maximization and basically tell you how we can get composable courses for the task of diversity maximization. Okay, so let's see what this problem is. Okay, so there are many scenarios where we are given a set of objects and we would like to pick few of them that have maximum diversity. Okay, so let's see a few examples. For example, we might be searching for a query in Google and we like Jaguar, and we want to make sure that the set of results are diverse. It contains Jaguar as a car and also Jaguar as an animal. If I do the same search which is squash, I see that all of them are like all the results in the first two rows are from squash as a vegetable and not squash as a sport. And if I search for the word scientist, I see that all of them are with white quotes. Okay, so it doesn't include computer scientists, for example. And there are actually a lot of other practical scenarios. For example, in a recommendation system, there's a user that is reading an article or buying an item, and we would like to offer a few other options based on what the user is reading or purchasing. It also has applications in summarization and so on. So in all these applications, we want to use a small subset of points that are diverse. Okay, that somehow represent the larger population. And so let's first see how we model such problems. Okay, so for example, we have a set of images. So what happens is that we normally map these images or documents or the objects in general to points in a high dimensional space using their feature vectors. Okay, so for example, if we have an image, a simple mapping is that maybe for each pixel in this image, I assign a coordinate, and based on its value, based on the RGB of that value, I assign a number in that coordinate. Okay, and the idea is that basically if two images are similar, then their corresponding points are closer to each other. Okay, so the distance between the points somehow show the similarity between them. And now as the inputs to our theoretical problem, we're given the following. We're given a set of n points in a d-dimensional space. So d is high, so we're in a high dimensional space, and we are also given this small parameter k. So for example, in the search application, maybe how many results do we want to report? Maybe like 10, right? And the goal for our problem, so the problem is as follows. We want to pick k points that have maximum diversity. How do we do it? Okay. And the first question you're asking is how are you measuring diversity? And there are several ways that people have used successfully to measure the notion of diversity. And let me name a few of them. For example, you can define the diversity between a set of points as their minimum pairwise distance. Okay, so if k is equal to 3 and I pick these 3 points, these are the closest, so I say that their diversity is equal to the length of this arrow. If I pick these 3 points instead, then there are 2 points that are even closer, so their diversity is lower. Okay, so maximizing this notion of diversity means that I want to pick k points such that no two of them are very close to each other. Okay, so this problem is NP-hard, but it's known that a greedy algorithm achieves a constant factor approximation for this problem. There are other notions of diversity. For example, you can define the notion of diversity more robustly as the sum of pairwise distances between the points. For example, if k is equal to 3, we want to pick k points or 3 points here such that the sum of these 3 arrows is maximized. So this is what I measure as their diversity. And if I pick these 3 points instead, then they are less diverse because the sum of these pairwise distances is smaller. Okay, so again, it's known that using a local search algorithm, one can get a constant factor approximation for this problem as well. And finally, the last notion that I want to mention is basically the notion of volume. So people also have used this notion as well. So here we want to pick k points that have the maximum volume. So basically the volume of the parallelepiped spanned by those k points is maximized. For example, if k is equal to 2 and I pick these 2 points, then the area of this parallelogram is what I measure as their diversity. And if I pick these 2 points instead, then the parallelogram formed by them is larger, and therefore I say they are more diverse. Okay, and so this problem is harder. It's known that there is no c to the k approximation for the problem even, but there's an algorithm that achieves like an e to the k over 2 approximation for the problem, but people use the greedy algorithm also a lot in practice for this problem. And although it's a harder problem to approximate, people use it because it depends on all the points at the same time. So it doesn't only depend on pairwise distances. For example, if the points are linearly dependent, then you get 0, and the more perpendicular they are, the more diverse we say they are. Okay, so as I said, this diversity maximization problem have been studied in the offline setting. So we know that for diversity maximization under different notions, we can get a constant factor approximation for the first two, and for the last one we can get like an exponential factor approximation. And what we have shown in our work is that basically no matter how many points you initially have, it's always possible to summarize the points into roughly size k and get a tight approximation factor for the problem. So first, let me tell you about our algorithm for getting a composable corset for the minimum pairwise distance notion of diversity. Okay, so first let's focus on the offline problem. So here, as I said, we have a set of endpoints and a parameter k. The goal is to pick a subset of size k with whose minimum pairwise distance is maximized. Okay, as I said, we know that a greedy algorithm achieves a constant factor approximation for this problem. So let's see what a greedy algorithm is and how we can prove like this approximation factor. So the greedy algorithm basically goes over k iterations, and at each iteration it picks the point whose minimum distance to the currently picked points is maximized. Okay, so maybe in the first iteration it picks some arbitrary point, in the second iteration it picks the point that is furthest away from the first point, and in the second iteration it picks the point, in the third iteration it picks the point whose minimum distance to the first 2 points is maximized. Okay, so now, and it repeats it for k iteration until it gets k points. So now let r be the minimum distance between these k points, okay? And it's in particular, it's equal to the distance of the last point that we picked to one of the previous ones. Okay, so now an observation is the following, that for all the other points, there exist the points that we picked, right, whose distance to them is at most r. Okay? So in particular, if this was not the case, then basically we would have picked another point in the last iteration. Okay? So for any point that we did not pick, there exists a point that we picked such that their distance is at most r. So now basically this is enough to show that this solution is a factor 2 approximation. So in particular, there exists, because the optimal solution has k points, there exists 2 points in the optimal solution whose minimum, whose closest picked points is the same, whose closest picked points among the first k-1 iteration is the same. Okay, and because we know each of these distances is at most r, the distance between these 2 points in the optimal solution is at most 2r. So we found 2 points in the optimal solution whose distance is less than 2r, and we know that our solution has value which is larger, which is exactly equal to r. So this means that our solution is a factor 2 approximation. Okay, so now let's show that the same greedy algorithm is also a good algorithm for computing a corset. In fact, it gives a corset with constant factor approximation. So what does it mean? I need to show that if I have multiple point sets and I run greedy algorithm on each of them separately to get this small subset, and let's take the union of these summaries, then the maximum diversity I can achieve by picking k points out of the union of these summaries approximates the maximum diversity I can achieve by picking k points out of the union of the original data set by this factor c. Okay, so let's see how we show it. So let's these be the original points that we have, and let's the red points be the result of running the greedy algorithm on each of them. Okay, so now our goal is to show that basically the union of these red points contains a solution that is relatively good with respect to the optimal solution. So now let's take the optimal solution, that is the set of k points. So this is the union of all point sets. Let the yellow points be a subset of size k with that has whose minimum pairwise distance is maximized. Okay, so now let me take back these each of the points in the optimal solution to their own subset. So now I consider two cases. Okay, so first let R be the maximum diversity among the points that I have picked in each of these solutions. So the minimum pairwise distance between the red points here, the minimum pairwise distance between the red points here, and the minimum pairwise distance between the red points here. I take each of them and I take the maximum over them. Okay, so now there are two cases. Either one of these solutions itself is relatively large. So if R is larger than the diversity of the optimal solution over, let's say, some constant 5, then we know that one of these red solutions themselves is good enough. Okay, so if the minimum pairwise distance between these four red points is large, then with respect to the optimal solution, then we are all done. Okay, so the other case is that R is much smaller than the optimal solution. So R is, let's say, smaller than the optimal solution over, let's say, 5. So now we want to show that the union of these red points contain a solution which is relatively large. So what I'm going to do is that I'm going to take the optimal solution, okay, and now I'm going to map each point in the optimal solution to a point from the corset that is closest to it. Okay, so now I'm going to replace the points in the optimal solution with their mapping. Okay, so instead of this point, now I'm going to include this one. Instead of this point, I'm going to include this one in the solution. And because this is the closest, because itself was a point in the corset, I'm going to keep these 2 points. Okay, so now the observation is the following, that because of the property that I talked about for the greedy algorithm, I know that the closest point in the corset to any point that is not in the corset is at most R. So this distance is at most R. And therefore, if the distance between, because the distance between any pair of points in the optimal solution is large, now this replacement by triangle inequality cannot make it much worse. So if I replace this yellow point with the red point here, the distance between this yellow point and this red point is not much smaller than the distance between this yellow point and this one. Okay, so replacing each point with its closest points from the corset cannot reduce the size, the value of the optimal solution by much. So it's still going to be within a factor of, let's say, 3. Okay. So that is our argument on the minimum pairwise distance. Okay, so let me now tell you how we can get a corset for the notion of volume. So how we can get a composable corset for volume maximization problem. And again, as before, the offline problem, just let me remind you that we have a set of endpoints. The goal is to pick k of them given a parameter k. The goal is to pick k of them such that the volume of the parallelepiped spanned by those k points is maximized. And now I'm going to show you that in fact the local search algorithm is giving a corset of size k with approximation factor of order k to the k. And in order to show that, as before, I need to show that if we have multiple point sets and we run the local search algorithm on each of them independently to get the smaller subsets, then the maximum volume I can achieve by picking k points out of the union of these small subsets approximates the maximum volume we can achieve by picking k points out of the original union of the original data set by this approximation factor k to the k. Okay, just to remind you, the local search algorithm is as follows. So we have a set of endpoints and a parameter k. We pick a subset of size k, an arbitrary subset of size k, and as long as we can find a point q inside and a point p outside, such that replacing q with p increases the volume, we will perform this swap. Okay, so again, I found a point q inside and a point p outside of the current set, and I see that replacing q with p increases the volume, so I will perform this swap, and until no such pair exists. So the solution I get is locally optimal. And first of all, we know that there are tricks to make the runtime of the local search algorithm to be polynomial. In fact, instead of starting with an arbitrary solution, we can start with a solution of greedy. And instead of replacing q with p whenever it increases the volume, it's enough to replace q with p whenever the increase in the volume is by at least a factor of 1 plus epsilon. Okay, so let me also mention that in order to check whether replacing q with p increases the volume, it's enough to look at the distance of q and p to this k-1 dimensional subspace that is spanned by all the other points in S except q. Okay, so whichever has, so it has k-1 points, so they form a k-1 dimensional subspace. So I look at q and p, whichever is furthest away from this subspace, it forms a larger volume parallelepiped. And the reason I'm mentioning this k-1 dimensional subspace becomes clear in a bit. So for now, let's see what is the overall structure of the proof. So as the first lemma, I'm going to show you that what the local search algorithm is in fact doing is that it's preserving approximately the height of the point set in all directions. Okay, so in fact, we show that it is giving 2k corset for the k directional height of a point set, which I will define shortly. And second, we show that basically we show a more general lemma relating the height to volume. Basically, we show that any corset for height gives a corset for volume. So any subset of points, any alpha corset for k directional height gives an alpha to the k corset for volume maximization. And if we just put these two lemmas together, it's so basically we replace the value of alpha in the second lemma with the 2k we have from the first lemma. So we get the following, that the local search algorithm produces a corset with approximation factor of 2k to the k. Okay, so as I promised, so I will show you these two lemmas, but as I promised, let me first tell you what this k directional height is. It's a very simple notion. Given a set of points and any k and the k-1 dimensional subspace G, the height of these points with respect to this subspace G is just simply the maximum distance of all the points to this k-1 dimensional subspace. Okay, and so now, what is a corset for k directional height? So we want a subset of the points that is preserving the height with respect to all k-1 dimensional subspaces. Okay, so we have a set of points originally. We want to pick a subset of size k, which are denoted by the green points, such that we have the following property, that for any k-1 dimensional subspace, if in the original points there exists one point v, whose distance to this subspace is L, then in the subset there should exist a point whose distance to this subspace is at least L over alpha. Okay, so if we have this property, we say that we have an alpha corset for k directional height. Okay, so the subset U is preserving the height of the points, the maximum height of the points with respect to all k-1 dimensional subspaces. Okay, so what we want to show is that basically local search algorithm is giving a corset for k directional height of the point set. Meaning that if we have a point set and run the local search algorithm on it to get a subset of size k, then although S has much smaller size than V, but it's preserving the maximum distances with respect to all k-1 dimensional subspaces approximately. Okay? So more precisely, for any k-1 dimensional subspace G, the maximum distance of the points in S to G is not much smaller than the maximum distance of all the points in V to G. Okay, and the approximation factor we're shooting for is just 2k. So let's see an overview of this, the proof in one slide by picture. So suppose that P is a point from the original points at V, and let's G be any k-1 dimensional subspace, and let's the red points be the set of points in the corset that is given by running the local search algorithm. Okay, so now we want to show that if all the points in the corset are close to this k-1 dimensional subspace G, then the distance of P to G cannot be much larger. So if all of these distances are at most x, we want to argue that the distance of the original point P to G cannot be larger than 2kx, and therefore showing this factor of approximation 2k. Okay, so how do we prove it? We take the we take the k-dimensional subspace that is spanned by all the points in the corset and project our point onto it. Okay, so now let's look at this projection. We know that because this is a projection onto the subspace spanned by all the points in the corset, we can always write this projection as the linear combination of the points that are in the subspace. Okay, so what we show is that basically by using the properties of the local search algorithm, moreover, we have the property that all the coefficients have absolute value at most 1. So all the coefficients are small. Okay, and basically this uses the fact that if for some specific alpha I this was not the case, then at the end of the local search algorithm it preferred to pick P over Qi. So it didn't happen because the solution was locally optimal, and this is enough to show that basically alpha I has absolute value at most 1. Okay, so we have this property, and now we just use a triangle inequality. So because all these Qi's have distance at most x to G, using triangle inequality, the distance of P of H to G cannot be larger than 2kx. Cannot be larger than kx. Okay, so their k term, each of them is at most x, so the distance of P of H to G is at most also kx. And with similar kind of arguments, but a little bit more work, we can also show that the distance of P to P of H is at most kx. And now putting these two together, it means that the distance of P to G cannot be larger than 2kx. So again, we use the triangle inequality. Okay, so this basically shows the proof for the first lemma, and now let me tell you how we get the second lemma. So this is a more general lemma saying that any subset of points that is preserving the height of the point set is at the same time preserving the volume. Okay, so again, let me show it by picture. So let's let the blue points be the union of all the points that we have, and let the red points be the union of the corsets. So these are the points that preserve the k-directional height of the point set. So what we want to show is that basically these red points contain a solution that have large volume as well. Okay, so for that, let's take a look at the optimal solution. So these are the set of k points from the original point set that have the maximum volume. So the green points are a subset of size k from all the points that have the maximum volume. And now I want to show that the red points also has a subset of size k whose volume is comparable to the green ones. And I do it as follows, basically. I'm going to go over all the points in the optimal solution one by one, and at each iteration I replace a point in the optimal solution with a point from the corset, and argue that this does not decrease the volume by much. So I do the following. I look at the first point in the optimal solution, and now I look at the k-1 dimensional subspace that is spanned by all the points in the corset, by all the points in the optimal solution except O1. Okay? And now I'm going to replace O1 with a point from the corset that is furthest away from this subspace. Okay, so because the red points preserve maximum distances to all, including this particular k-1 dimensional subspace, I know that replacing O1 with this new point does not decrease the distance and therefore the volume by much. So by at most, it is decreased by at most a factor of alpha. Okay, so I do this replacement. Now I go to O2. And again, I replace O2 from the point from the corset that is furthest away from the subspace spanned by all the other points in the solution except O2. And then I repeat this process until I have replaced all the points in the optimal solution with points from the corset. So I started with the optimal solution and I ended with k points from the corset. At each iteration, the distance and therefore the volume decreased by at most a factor of alpha. And because there were k points and I repeated this process k times, the decrease in the volume happened by at most a factor of alpha to the k. Okay, so this basically shows that so this basically finishes the argument and shows that the local search algorithm is in fact giving a composable corset of size k with approximation factor order k to the k. So then we were looking at whether it is possible to improve our corset. Is it possible to get a corset that has better approximation factor? And we were able to show that no, even if you allow the size of the corset to depend polynomially on k, let's say k cubed or k squared, then it is not possible to get a corset that has approximation factor better than order k to the k over 2. Okay, and in the later work, we basically matched this upper bound, so we improved the approximation factor of the algorithm to depend on k to the k over 2. Okay, we also analyzed the widely used greedy algorithm in practice, and we finally implemented all these algorithms and compared their performance on real-world data. We showed that basically the local search algorithm is also performing well on in practice. Okay, so with that, let me zoom out a little bit. So today we talked about the notion of corsets and composable corsets as methods for summarizing the data. And we showed, so we talked about different notions for capturing the concept of diversity, and we showed how we can get composable corsets for maximizing diversity under two different notions. Okay, so more broadly, composable corsets have been used a lot due to their applicability. They have been defined in different contexts. For example, in the context of graph algorithms, how can you, for example, summarize a graph so that the value of the maximum matching is preserved approximately? Okay, variants of composable corsets have been defined. For example, randomized composable corsets, where the partitioning of the input into these multiple parts is also done randomly. Okay, and so there, let me conclude the talk by a few open problems. So at the end of the day, what we ideally would like to do is that how we can, to answer basically what kind of problems admit such efficient summaries and what kind of problems do not. And we have shown that not all problems admit such summaries, so it's interesting to see what problems admit composable corsets. But at the same time, it's interesting to see what is, like if we allow, for example, the randomization, then can we get better corset? Or if we allow the size of the corset to grow a little bit, then can we get a much better approximation factor? Ideally find the optimal trade-off between the size of the corset and the approximation factor. Okay, and I also said that having a composable corset for a problem means that we have a streaming algorithm and a distributed algorithm for the same problem, but they're not necessarily optimal. So what is the relation here, and what is the best algorithms in other models for these problems that are that we discussed here? Okay, so with that, let me thank you all for listening to the talk, and feel free to send me an email if you have any questions, and I hope you enjoyed the talk.